Analytical Chemistry 1, Lesson 36. Titration is perhaps the most fundamental experimental technique in analytical chemistry. It is capable of providing two essential pieces of information about an unknown acid-base sample: how much of it is present in the sample, and what is the value of its pKa. We will calculate acid-base titration curves with the goal for you to become familiar with their shape so that you can readily interpret one and quickly point to the features that provide the desired information. The simplest curves are those that arise when a sample with a strong acid in it is titrated with a solution that is a strong base. We start by considering a sample that is 50 milliliters of nitric acid at a concentration of 0.04 molar. This is called the analyte. We add another solution called the titrant in a carefully controlled and measured manner. At this point, we are restricting our discussion to an analyte that is strong acid and to a titrant that is strong base. The chemical reaction that is occurring is the reverse of the autoionization of water. This reaction has an equilibrium constant of 10 to the plus 14. It's plus 14 because it's the reverse of autoionization. And that is a very large value. We can readily conclude that the reaction goes to completion and make the reasonable assumption that any amount of added hydroxide will react the stoichiometric amount of hydronium ion. When we have added the exact stoichiometric amount of titrant as there was in the analyte, and if we are able to measure when that occurs, then we can know how much analyte was present in the original sample. The point in the reaction when this balance occurs is called the equivalence point. Finding the volume of added titrant needed to reach the equivalence point is the key outcome of every titration experiment. Now, there are four types of calculations that we are going to be doing in order to create a titration curve. At the beginning, what is the analyte pH before we start the titration? This is just the kind of calculation we have been doing up to this point. In the region before the equivalence point, here we have a mixture of unreacted analyte in an increasing volume of water. At the equivalence point, in the case of a strong titration, this is trivial. The pH equals 7 simply because the reactant involved is the autoionization of water. There could be differences because of the presence of counterions from the titrant and analyte. They would produce an ionic strength that may be sufficient to affect the activity of the species involved. But since we're not incorporating activity at this point, well, finally and beyond the equivalence point, this is just the dilution of the excess added titrant. Let's titrate this 50 milliliters of 0.04 molar solution of nitric acid with 0.06 molar sodium hydroxide. At the beginning, the solution is 0.04 molar in a strong acid, so H plus is equal to 0.04 molar and pH is 1.398. It can also be useful to note the amount of analyte present at the beginning. 0.04 molar times 0.05 liters is 2 millimolar. Add 1 milliliter of titrant. The moles of added base, 0.001 times 0.06, or 6 times 10 to the minus 5 moles. This reacts fully with as much analyte as it can. The remaining analyte is 2 millimoles minus 0.06 millimolar, 1.94 times 10 to the minus 3 moles. Now there's less acid than at the beginning, so we can anticipate that the solution's pH has increased, becomes less acidic. But wait, the volume of the solution has also increased due to the added titrant. So not only is there less analyte, it is also in a larger volume. The pH is changing because of two reasons. Some analyte has been removed by reaction, and there is dilution. Volume now is 50 plus 1, or 51 milliliters, and with this remaining amount, the concentration now is 1.94 millimole divided by 51 milliliters, 38.04 millimolar, giving a pH of 1.420. Add another milliliter. Reaction leaves 1.88 millimoles. Dilution gives a volume of 52 milliliters. Analyte concentration is now 36.15 millimolar. pH equals 1.442. Add another milliliter. Reaction leaves 1.82 millimole. Diluted volume is now 53 milliliters. Analyte concentration is 34.34 millimolar. pH equals 1.464. You probably see the pattern by now. When we've added 15 milliliters, the reaction leaves 1.1 millimole in a diluted volume of 65 milliliters, so that the concentration is now 16.92 millimolar, giving a pH of 1.772. This can continue, but it's just more of the same. It's a lot better to use a spreadsheet to do all of these calculations for us. And it would be nice to craft it into a single equation. I like to do all the steps first so that you can see what is happening. But here's another way to look at the calculation. The original analyte concentration decreases for two reasons: reaction and dilution. The dilution factor is simply the ratio of the original volume to the volume at this point in the titration under consideration. Let's use VAT as the volume of added titrant at this point in the titration. Now the dilution factor has this form. So to determine the reaction factor, we need to determine the volume of titrant that will be needed to reach the equivalence point. In this case, since the stoichiometry is 1:1, we need to know the volume needed to deliver the moles of titrant that equals the moles of analyte. Now this is a C1V1 equals C2V2 type of problem. In this case, we have 50 milliliters times 0.04 molar divided by 0.06 molar, or 33.3 milliliters. The equivalence point will be reached when this volume of titrant has been added. Let's call this V sub EP. The ratio we use to determine the amount of remaining analyte is VEP minus VAT over VEP, the ratio of the titrant volume that remains to be delivered divided by the equivalence point volume. The final equation is the product of these two ratios, reaction and dilution, with the original analyte concentration. Turn it into pH, graph pH versus titrant volume. This equation is valid before the equivalence point. As we approach the equivalence point, we start to approach a pH of 7, which is the region wherein we need to use the quadratic expression that includes the influence of water. But we are able to get close enough without the extended equation. It would be extremely small values of titrant before the equivalence point before we would require it. If you work through the equations, you will find that unless the titrant is very dilute, it is only within a fraction of a drop where there are meaningful differences. So we do not generally worry about it, just jump to the equivalence point. And so at the equivalence point, as stated before, in the case of a strong acid or base being titrated by a strong acid or base, the equivalence point always occurs at pH equals 7. When we introduce weak acids or a base as the analyte, you will see that this is no longer true, but for these cases it is. Beyond the equivalence point, now we are accumulating unreacted titrant. The pH rises, in this case, because the added hydroxide no longer has excess hydronium with which to react. Now it is just adding strong base to water. We will create a single equation like before. The difference is that the reaction is now completed and we just have to consider the amount of base added in excess of the stoichiometry needed to reach the equivalence point. And then we need to account for the dilution of the added titrant into the solution. We will work with the original solution volume, the added titrant volume, and the titrant volume needed to reach the equivalence point. Also, we previously were scaling the original analyte concentration, but now we will be scaling the titrant concentration. The solution pH is now being controlled by the dilution of the titrant rather than the analyte. And in addition, note that we are now finding the hydroxide concentration and will need to convert it to find the hydronium and hence the pH. We only have a dilution factor this time. The titrant concentration is diluted by the factor of the titrant volume added in excess of the equivalence point, divided by the total volume, which sums the original analyte volume and the added titrant volume. This is the formal base concentration, and since we have a strong base, we equate it to the hydroxide species concentration. Solve for pOH, subtract from 14 to get the solution pH. So, what does this all look like? Here's the titration curve using the values discussed above. Analyte concentration is 0.04 molar, titrant concentration is 0.06 molar, and light volume is 50 milliliters. This S-shaped curve is said to be a sigmoidal curve. The key to the success of a titration experiment is how sharp the curve transitions from low pH to high pH. In this region, the curve is not exactly vertical. In the case of strong titrations, however, it is pretty close, but we will see other examples where the transition is much less abrupt. For the special case of strong titration, the equivalence point is when the curve is at pH equals 7. If you were carefully modeling this curve, you would find that the second derivative of the curve equals 0 at this point. It is a point of inflection. The slope of the curve is positive everywhere, but as it gets closer to the equivalence point, the slope becomes more and more positive, reaching a maximum at the equivalence point. Beyond that, it starts to flatten out again, though it is always positive. In more difficult situations, scientists will calculate from the data a first and second derivative and plot those as they try to get a better estimate of the titrant volume at the equivalence point. But with this curve, it's fairly easy to draw a vertical line through the equivalence point down to the x-axis and read off the volume of titrant added at the equivalence point. If the analyte concentration were unknown, determining the titrant volume at the equivalence point would allow you to calculate the unknown concentration. Now, what if the analyte was a strong base and the titrant was a strong acid? Let's find the titration curve where the analyte has a strong base concentration of 0.03 molar, an analyte volume of 25 milliliters, and a strong acid titrant with a concentration of 0.025 molar. This time the titrant concentration is less than the analyte, so the equivalence point volume will be greater than the analyte volume of 25 milliliters. The starting pH is just that of the formal base concentration. The pOH is 1.523, so the pH is 12.477. The equivalence point volume this time is 30 milliliters. Also, the pH starts high and decreases as the added titrant volume increases. We have the similar equations except that we find hydroxide at the beginning and must convert it to pH. The equivalence point again occurs at pH equal to 7. Beyond the equivalence point, we have the dilution of the excess added titrant. And here's the graph of this titration. Draw a vertical line through the equivalence point down to the x-axis and read from there the volume of added titrant. This can be used to find an unknown analyte concentration.